This lecture is going to be on how your voice creates sound and how your ears interpret that sound. So we're going to look at both voices and hearing. So sound, it's all in waves. Your ear is sensitive to waves found within a particular frequency. Voices are composed of a wide range of frequencies, giving people distinct voices. Voices are complex sounds created by the superposition of multiple frequencies. So if I consider these three examples, Anne, John, and Beth, that they each have different combinations of frequencies that make up the end result of what their voice sounds like. That they have these different frequencies that all kind of make it up. So we each have our own individual frequencies that are the fingerprints that make up our own individual voices. So complex sound, it's made from many frequencies. So that's what we create. Our voices are complex sounds. So when we speak, we've got all these different frequencies kind of added together. And that's what we call the superposition principle. That if I have a frequency of 264 hertz and 330 hertz and 396 hertz, they add and subtract out, meaning they constructively and destructively interfere. And this is what we call superposition. Superposition is really the interference pattern of all the ups and the downs, and we get this net effect of crests and troughs. So the brain then breaks down the complex sound into perception of each separate frequency. And so we hear this voice, we only hear it as one. We only hear it as the superposition sound related to our ear. So let's emphasize superposition principle for a moment. Waves are always adding and subtracting from one another. The displacement due to two or more waves that pass through the same point in space is the algebraic sum of the displacements of the two or more waves. In other words, you just add or subtract them. So we learn this. We learn this in the form of interference. Now we're going to put it together and apply it to sound. Constructive interference. The waves reinforce each other and add together, where the amplitude gets larger. So here I have wave 1 in the same phase as wave 2, and we see that the crests add together and the troughs add together. So the net effect, or the law of superposition, says that it's got a higher crest and a higher trough. So we recognize the superposition, the net effect of both of the waves acting simultaneously. Whereas destructive interference, the waves cancel each other out, where the amplitude gets smaller. So here I have wave 1 and wave 2. These are 180 degrees out of phase of one another. So they are in opposite locations. So their superposition principle, meaning the net effect of the wave, crest and troughs, are going to add together. In this case, they're going to subtract from one another. They will destructively interfere. Then they will lead to this net flat line, this zeroing effect. And this is kind of what happens. This is the exact principle of noise-canceling headphones, if you've ever had them on. There's a noise created at different crests and troughs, right? Different frequencies, different highs and lows. And you get this anti-noise. You get the canceling, the noise-canceling headphones are actually creating this anti-noise to offset the crests and the troughs. And it leads to a net quieting effect. It's a form of destructive interference. So here we can look at superposition principle of water waves. We're seeing both constructive and destructive interference patterns. And these are just two drops or two locations of water that are oscillating, and you can actually see this really nice pattern. The white are the maximums, and the black are the minimums, and blue is the zeroing effect. And so you get these circular waves here, and where they, let's just say, overlap one another, they add together, right? That's your maximums, and the black is where they cancel one another out. The blue is where they cancel each other out at zero. So the black is going to be where the crests the troughs constructively interfere. The white's going to be where the crests constructively interfere. Let's look over here. I just want to emphasize superposition. If I have wave 1 and wave 2, and they are in phase, you see that they add together, constructive interference. And here, if I look at two waves that are 180 degrees out of phase, they cancel out. But realistically, you don't get this perfect pattern all the time. It's normally an irregular pattern. You don't get these perfect crests and troughs that align, and you definitely very rarely ever get a flat line. So what happens here is, I think this picture right here is going to be more reflective of what you would really see. So notice I have this really long, this larger wave here. And here I have a smaller wave. I have a higher frequency here and smaller amplitude. And when these are constructively interfering, notice this crest added to this crest, it's going to be the highest net position. And where it interlaps or intersects right here, it's also intersecting right here, it's going to be intersecting right here. Your resultant is your net effect. So therefore, this would be the superposition, kind of the resultant alignment of the crests and the troughs from both wave 1 and wave 2. This is more realistic. They're going to be these irregular patterns for the most part. And notice down here, you get these bumps and the squiggles in here. Here we'd add this here with this crest here, so therefore your net effect would be this kind of blurb down here. But I do want to make sure that you see that here, this net negative is going to add with this net positive, or it's going to be the net difference of them. So you'll see that it's actually not that far from your equilibrium line. So this net effect, or this resultant effect, is the result of your superposition principle. So let's go back and summarize frequency and pitch. A person with a high-pitched voice creates sounds at higher frequencies. So the higher the frequency, the higher the pitch. So higher frequency tells me that I've got more oscillations per unit of time. And a lower frequency has lower number of oscillations, or in this case we would have a larger wavelength in some period or unit of time. So high-pitched sound occurs at high frequencies, and low-pitched sound occurs at low frequencies. Higher the pitch, higher the frequency, lower the pitch, lower the frequency. So here I can associate frequency to energy. The greater the frequency, the greater the energy. So if I have, in this case, I have 3 oscillations per unit of time, it's going to have 3 times the energy than this one here. If I look at these as standing waves, my fundamental, my second, my third harmonic is going to have 3 times the energy as my fundamental. And when I look at amplitude and energy, the smaller the amplitude, the lower the energy. The larger the amplitude, the larger the energy. So let's look at how a person creates sound. Let's talk about our voice box for a second. The human voice is produced in the larynx, a part of the throat. There are 2 small tissues that act as our vocal cords. As we speak, muscles in our larynx tighten and the vocal cord narrowing the opening. The diaphragm pushes air from the lungs through the vocal cord in pulses, producing vocal sounds. This pulse train is shaped by the resonances of the vocal tract. The process of air moving through the vibrating tract of oscillating membranes creates sounds that end up in the esophagus and get amplified by the mouth, much like that of a megaphone. So the tighter your vocal cords, the more rapidly the vocal cords vibrate, the higher your pitch. A person's individual and unique voice is reflective of the nasal cavity, the oral cavity, muscles in the neck and face, the tongue, along with teeth and cheek movements. So you can actually have a different pattern in the way in which you say a word. That's going to be all of these features and factors that are going to have a net effect on your voice. It's not only the air being pushed through your lungs, or pushed out of your lungs by your diaphragm that travels through here. It's not only the vibration of your vocal cords. It's not only the oral cavity, but it's a combination of all of these. And that's why most people have very unique and uncommon voices. There's just something about them that any one of these could be a little bit different, or different tightness of vocal cords. And we would say the same word and we would have a different frequency pattern and a different loudness in the way we say a word, such as father. So there we were done with, here we're talking producing sound. Now let's talk about hearing sound. We'll talk about the ear structure. So here's a picture. We're going to be looking at 3 parts. We've got the outer ear. This is what collects sound. This is the pinna. This is actually kind of a reverse megaphone. Just as your mouth amplifies sound, right? So it's like a voice from your esophagus amplifying sound. Your ear takes little bits of sound and then makes sense of it. So it's like a reverse megaphone. Then your middle ear transforms the sound from air into vibrations, which involve bones in the inner ear that translate this. And then your inner ear converts the nerve impulses that are sent directly to the brain. So this picture is going to be talked about a little bit more in detail. Watch this little video. It's kind of short and sweet, but it's very well done. But we're going to look at how sound entering the ear is funneled into your ear canal, and it goes through a series of, let's just say, vibrating interactions to then, before you make sense of it, and you're able to respond to it. So how does a person hear sound? Well, the ear flap, the pinna, is designed to catch sound. It also helps a person identify the direction the sound is coming from. Once sound is caught, it is funneled into the ear canal and toward the eardrum, the tympanic membrane, much like that of a drum. This tiny flap of skin acts just like the diaphragm in a microphone. The compressions and rarefactions of sound waves push the drum back and forth. Higher pitched sound waves move the drum more rapidly. In the loud sound, move the drum a greater distance. So the louder is really going to be looking at in terms of net amplitude. The cochlea is by far the most complex part of the ear. Its job is to take the physical vibrations caused by the sound wave and translate them into electrical information that the brain can recognize as distinct sound. This is how we make sense of our world. We take these vibrations and we create them. Your body is biophysically designed to translate sound waves into an electrical signal that goes to your brain, where you process what that sound is and make sense of it, and then you respond to it. So here's a nice summary on speaking and hearing. Just a couple nice YouTube videos I found on YouTube that are good animations of what's going on. Hopefully that made sense.